So here we are at section 5.9, simple system analysis. And so this is where we bring together the concepts of our system curves and our pump curves. And when we're looking at a pump has to be capable of meeting the static head requirements, overcoming any head losses, overcoming the pressure, or adding enough pressure head to the system so that we can meet pressure or delivery pressures for the end users. And it also has to be able to deliver the flow rate, okay? So all of those things are dependent on the system curve. And so we present that on a system curve, and when we graph out the system curve, what we can do is overlay the pump curve on it, and we can see whether or not the pump is a good fit for that particular system. So we're going to go on to the next slide here. So this is how we do it. Basically, what we're going to do is we're going to graph a system curve, and then you create the points of the system curve by doing an analysis of your system. So I'm going to go through and give an example of how you do that. We've done some of that already, but we haven't actually put the data in the form of a curve yet. We've just done the analysis, the hydraulic analysis of a system. We haven't graphed it. So basically in this slide here, excuse me, I've given you the process through which you create a system curve. So basically you identify the range of flow rates, basically from 0 to kind of your maximum flow rate that you would see in the system based on, fire flows, day-to-day use. So you'd estimate that. And then you would basically choose 4 to 5 flow rates. And then you would do the analysis of your system and figure out what are your head requirements. So you'd look at both your elevation head requirements, your pressure head requirements, and your head losses. So one of the things you'll notice, and I've given you a little example table there, is your elevation head requirements don't change. You're not going to be pumping, your end users aren't moving around, so they're always going to be at the same elevation. Your pressure head requirements are generally constant also, because people want a constant pressure. They want 450 kPa or 500 kPa. That's what they want. And then the thing that does change though is our head losses. So as our flow rates go up, our velocities go up, and so our head losses go up. So the amount of head that our pump has to be able to deliver at increased flow rates also increases. So then once you have that all figured out, you graph it and you create your system curve. So we're going to do this process on the next page for an example here, and you are going to need your Hayes and Williams nomograph. So can you please break those out, and we will do this together. All right, so for this particular example, we have a pump that's pumping to a reservoir that's located at the end of a horizontal pipe. So when we're looking at this, and I'm going to label these points. This is point 1. And then here, at the surface of the water, that is point 2. So the first thing you're going to want to do is you're going to want to set up a table. And so your table is going to have, in your first sort of column, we can put our velocities, which are going to range from 0 to 5 meters per second. So if we pick velocities, and then we can figure out the Q that goes along with it. And then we can figure out our elevation head, our pressure head, our head losses. Ooh, and I'm running out of room. And over here, we can put our total head. So when our velocity is 0, our flow rate is 0. When our velocity is 1, 2, let's see, our maximum, let's do 5, and we'll do, I don't know, let's do 3.5. Sorry for the small writing, there's not a lot of space on here. So what I need everybody to do now is figure out what the flow rate is going to be when your velocity is each one of those 4 velocities. And you all remember how to do that with your Q equals VA. And your area here is going to be dependent. You have a 12-inch diameter pipe. So you have to figure out what the area of your pipe is. Does anybody have an area they would like to share? Yeah, we definitely need everything in meters squared. Can anyone confirm Mike's number? Okay, we're getting some thumbs up. Okay. So when you're ready, I'm also going to need the flow rates for each one of the velocities listed. So 0, 1, 2, 3.5, and 5. Okay, so Sawyer's thrown out same. So people seem to be liking that. 0.07, 0.14, 0.25. Wow, my writing's really bad on the screen. And 0.35. I might have to go and do this on a bigger screen. Now, does everybody, yeah, and that's in cubic meters per second for sure. So that's what our flow rate is. Now, what is the elevation head that this pump is having to lift the water to? And it's not a trick question. Yeah, it's 0. So we basically have 0. Our pump has to do no work lifting the water. Okay, now how much pressure head does our pump have to add in this particular scenario? At 0.2. And again, I will tell you this here, the reservoir is open to atmosphere. All right, correct, Wanda. So we're not having to maintain any pressure for our end user, which at this point happens to be a reservoir. So far, the only thing our pump's got to do is deliver a flow rate, okay? But what we have to do now is we have to figure out what the head losses are that we have to overcome. So what are the head losses when our velocity is 0? Yeah, definitely 0. We have no moving water, we can't have any head losses. So now, for our next point, we are going to have to use the Hazen-Williams nomograph, a flow rate of 0.07, a diameter of 12, a C equals 130, to figure out a slope. And once you have that slope, you times it by the length of the pipe in order to figure out what the head losses are. So I'd like everybody to break out their nomographs. And when you're ready, maybe someone could tell me the slope when the velocity is 1 and the head losses when the velocity is 1. It's okay. All right, so it seems like people are getting 3.5-ish per 1,000 meters for the slope of number 1. Okay, so then you're going to times that by 5,000, and you'll end up with the head loss for when your velocity is 1. So because our pipe is 5 kilometers long, you should end up with a head loss of something like 17.5. Yeah, great. No, you need to do that exact same process for the next 3 points. If we were in class, I'd divide you up in rows and have each group do a different head loss, but it's pretty hard to divide up people that can't see. So Quinn, is that 60 meters of head loss for velocity 2? Okay, does anybody want to agree with Quinn? How are you doing out there, folks? $50, $60. Are you guys all looking at the same graph? Yes, there's a nomograph on Moodle. So Stephanie, I'm looking at your number and it seems to be quite a bit out from where everyone else is being. So I think for the sake of argument here, okay. All right. Well, just for the sake of this, so we can all move on, I'm going to keep it at 60 because that seems to be in the range of where people are getting. So can I have like half of you out there do 3.5 and the other half do 5? So everybody with the last name that falls before, so from A to M does 3.5, and then from N to Z, last names does the 5s, meters per second. Okay. All right, 200 and 325. Can I get some others from the groups to just confirm those numbers in and around that range? Doesn't have to be exact. Okay, good, thank you, Erin. Okay, so now you are going to graph a system curve, which basically graphs the total head and the total flow. Now for us, if we add up all the heads, we get 0, 0, 0 is 0, and 0 plus 0 plus 17.5 is 17.5, and then 60, 200, and 325. Okay. So now what we're going to do is we are going to, that's the total head, Kyra. So that's all the total dynamic head that the pump has to add to this system. It's the requirements that the system is demanding. Okay, so what I'm going to do is I'm going to move to a blank screen, folks, and then we're going to graph this. So if we take a look at our first point that we're graphing, so we need to go up to a total of, let's say, there's 300, 150. Well, 300. Whoops, sorry, that would be. Then our maximum flow. So if I'm going to graph my first point, my head is 0 and my flow rate is 0. My second point, my flow rate is 0.07, which is somewhere around here. And then my head that I'm adding is somewhere here, 17.5 meters. Then I'm at 0.14, which is somewhere here. And the head I'm adding is here, about 60. And then I'm at 0.25, which is here. I'm having to add 200, which puts me about here. And then at 0.35, which is here, that I have to add 325 meters of head, which is somewhere here. And so I end up with a system curve, which looks remarkably like the system curves that you created in your lab. So when we look at this particular system curve, the first thing that we'll notice about it is that it starts at 0 meters of head. So that means that there are no static head requirements for this pump. That means when the flow is not happening, this pump does not have to put any energy into the system. All of the requirements of this system come in terms of the dynamic head or head that's moving. Does anybody have any questions about that? All right, so we're going to do this exact same process one more time, but we're going to do it on a system that's got a little bit more complexity. Yeah, I know. I'm sorry, Jongsun. But you're going to see it's going to go a little bit faster because we've done quite a bit of the work already. So I'm going to go back into our PowerPoint. It's just loading. Give me a second here, folks. So we're going to follow these same steps that we just did for this system that we have presented to us. And we're going to create the same sort of chart. And we're going to analyze the system. Here's point 1. Up here, at the surface of our reservoir is point 2. And we're going to see what are the requirements of the pump. So what does the system need? So first of all, again, we start with our velocity. Then we figure out what our flows are. Then we look at what the head requirements are for our pump, like how high does it have to lift the water, the elevation head. Then we figure out what our pressure is, our pressure head requirements are. Then we take a look at what our head losses are, and then we can figure out what our total head requirements are for our system. So just for convenience sake here, we are going to use the same velocities, 0, 1, 2, 3.5, and 5. And because our pump is the same, it's a 12-inch PVC pipe, our flow rates are going to be the same as the last example, so we don't have to recalculate those. So that makes things a little faster. But now we have got a little bit more needs of our system. So when we take a look at this system, what's the elevation head that this pump is going to have to overcome? Yeah, 85 meters. So we've got, regardless of what the flow rate is, this pump is always going to have to at least give the system 85 meters of head because it has to lift the water up that high. Now, what are our pressure requirements in our reservoir? Yeah, still zero. We're open to atmosphere, so the pump doesn't have to deliver any pressure head to our end user. Now, it also still going to have head losses. Now, conveniently for us, as with the last example, the pipe is still 5 kilometers long. It's still the same pipe. So our head losses are going to be the same as what we observed in the previous example, so we don't have to recalculate them. Yeah, yes. So now our pump has to not only supply enough energy to move the water, so give us the flow rate, it has to lift the water to 85 meters of head, and it has to overcome any head losses. So then our total head losses are going to be the sum of our elevation head, our pressure head, our head losses. And so we have 85, and then we have, I don't know, whatever the next ones are, because I can't add. Okay, so 102.5. Oh, thanks, Josh. 145, 285, and 410. So you're going to go through and you're going to graph these just like we did in the previous example and create a system curve. Yes, that's exactly it, Sawyer. It is the same curve, but with 85 meters of static head. So if we draw that, and I'm going to go on here again. Here's our and we've got our head here. So we start at 85 meters. This is 0. And our flow rate goes up to 0.35. And then our maximum is going to be 410. And you guys are going to graph out the points. You'll graph out your points. But you'll end up with a curve that is the exact same shape as the previous curve, but it starts at 85 meters. So this is your static head. And this requirement here, which includes your static head, is your total dynamic head. All right, does anybody have any questions about this before we move on to our next example? Is it okay for me to go back to the PowerPoint? Okay. Just not sure how much time people need for writing here. I can't see you. All right. So here's another example. And you'll notice we keep building on our previous example. So in this particular scenario, we have the requirements of our pump are going to have to meet. It's going to have to lift the water to 85 meters of elevation. It's going to have to overcome the head losses. But in this scenario, it's also going to have to make sure that the end user has pressure. So it's going to have that line that we had that was the pressure head, which was previously 0 in the last two examples. We're actually going to have a head requirement for pressure. So again, we do the exact same thing where we calculate our V, we calculate our Q, we calculate our ZH. This time we're going to have a pressure head, and we have our head losses, and then we're going to have our head total. So column 1, column 2, column 3, so this is going to be 85 all the way down. And our flows are going to be the same as they were before, 0.107, pardon me, 0.14, 0.25, 0.35. Our velocities were 0, 1, 2, 3.5, and 5. But this time, our pressure head, we have to meet pressure requirements. So here we say we need to meet 300 or 550 kPa. So what is that in pressure head? Okay, Quinn's throwing out 56 meters of head. Does everybody want to agree with that? Yep. Okay, people like that number. So like the elevation head, the pressure head doesn't change. So for all of these points, it's going to be exactly the same. And then again, our head losses from the previous examples, because we've got the same pipe. The pipe is still a 12-inch PVC with a C equals 130. It's 5 kilometers long. We figure out what the head losses are. That's not going to change. So we have 17.5, 60, 200, 325. And then we have our total head requirements, where we are going to add our elevation head, our pressure head, and our head losses to come up with the total head that our pump is going to have to overcome for this particular system. So 141 for the first one, and so on. When you guys are ready, 141, 159, 201, 341, and 466. Great. And then we're going to graph that again. And so it's the same idea as we had on the previous ones, where we graph our head versus our flow. But in this case, instead of starting with a static head of 85, we're starting with a static head of 141 meters. And then our curve goes up from there. Because your pressure head is equal to your pressure divided by the specific weight of water. So when you take 550 and you divide it by 9.8, you get 56 meters. You're not dumb, Kyra. There's a lot going on in these questions, and it's easy to lose track of all the steps and formulas that you know. All right, so how's everybody doing out there? Do you need a bit more time, or is everyone ready to move on to the next concept? Don't cry, Quinn. Aw, you can do it, Kelsey. I know it's been a big day. It's a lot of physics for one day. I think we'll call it after this problem, I think. Oh, okay. Yeah. Just to say, Gemma, when you go back, if you look just a couple slides back, whoop, here's the steps you have to follow. Okay. So that is the plan. And it's the same every single time. Okay. So if you did that, I think people would probably take you out and buy you a beer. Oh yeah, I guess we can't go for beer right now, can we? There's no bars open and we're not allowed to get together as a group. So you'll have a beer credit some time. Okay. All right. Yeah, I think they did declare the alcohol store as essential services. All right. So, folks, here's the next thing that you will create a graph that looks like this. Whoop. And so you're going to have your, actually, maybe I'll keep it that color. You're going to have your system curve, which looks something like this, and it starts at 141, and its maximum flow was 0.35. So you'll have a curve that looks like that. And then the next thing you're going to do is you're going to graph your discharge, your pump curve on here. So again, you're going to go starting at, and I'm going to put the pump curve in blue. And so this is 300. And so our first point would be here, and our head goes down to, see, that's 150. So there's sort of, let's say that's 100 and 0.32. So you're going to end up with a pump curve that looks something like this. And you're going to graph all the points that are on the curve that are given to you in the chart. And then you're also going to graph your efficiency curve, which has got the peak efficiency at 0.15. And I'm going to put the efficiency curve in red. And it's going to have an efficiency curve that looks something like this. And our peak efficiency is going to be here. So I'm going to show you something that we haven't talked about so far, where the black is the system curve, the blue is the pump curve, and the red is the efficiency. Okay. I'm doing both example C and example D. The system curve example is example C, and the pump is example D. System curve is black. The pump curve is blue. Operation point. So that is where your pump is going to want to operate. And the idea is that you want your operation point and your best efficiency point to be very close together. Well, yeah, if you look at your best efficiency flow rate, it's somewhere over here, and my scale's not particularly great. But then your next step is to calculate your best efficiency range. And at very least, you want your pump operation point to fall within the best efficiency range. If it doesn't fall within your best efficiency range, then you do not want to use this pump for this system. Okay, so Sawyer says our best efficiency range is 0.06 cubic meters per second to 0.12 cubic meters per second. Well, no, actually, Sawyer, the BEP is at 0.15 centimeters per second. That's when our efficiency is the highest. So it's 73% at that point. Okay, so this should be 9 and 1, 8. So what's the flow rate here at our operating point? So Stephanie's throwing out approximately 0.26. I would say it's probably closer to Wanda's number than Stephanie's. Yeah, well, you can tell my graphing's not super fabulous, but if you're doing it to scale, it's probably gonna be closer to 0.26. Maybe even be a little bit lower. Okay, thanks. Sawyer says it's 0.18. Okay, so I'll adjust that. So then our best efficiency range goes up to here. So our operating point where they intersect goes up to approximately 0.18. So when we have high flows that are happening in this system, we would start to get outside of our best efficiency range. But if we're having lower flows, like flows that velocity, say around 1 meter per second, which is normal flows, basically what happens is our system curve shifts up and we'll be operating somewhere in and around here. Okay, so this pump isn't bad if our flows don't get into fire flow conditions. Once we start to get into that range, then we're going to have some troubles. Okay. So there's one more example, and it's hard. So what I'm thinking is we won't cover that in this course, and I won't give you that style of question on your final. So we will only do a single node analysis and not a 2-node analysis, like is on the example 5.9. So you guys can you cross that out? Example 5.9 from your PowerPoint that you have? And then, okay, Francine, can you explain how to find the best E range? The best E range is you take your QBEP and you times it by 0.6 to get the lower end, and you times it by 1.2 to get the top end. I kind of like Olay. It's very festive sounding. Okay, so everybody's crossed out question 5.9. And then when you go into your practice problems, do not do any of the 2-node analysis. Just do the single node analysis, please. I'm also going to email you my solution to this problem that we just did so that you can take a look at it. And okay, I'm going to do that right now. I'm just taking a picture of my solution. Yeah, I know. The Olay is kind of nice, isn't it? I don't know yet, Eric. Okay, this, of course, writer. Okay. All right, people, I'm just shipping you the example right now. It should be in your inboxes. There's going to be lots of math, Aaron. Yeah, exactly. So here, does everybody remember what a hectare is? All right. Well, if you don't want to use hectare again, you should go into the water wastewater side. All right. So I'm calling it there, folks. You've been awesome.